Sup guys, welcome to today's show. The logical next step is creating a free function which deallocates an existing allocation. So how do we do that, and what should we call such a function? I don't want to call it free because that will collide with the standard C library. Maybe we can destroy. Let's say we name it destroy. So we can make this a boolean because it can succeed or it can fail. If we use the standard C library functions like malloc and free, and we try to free an allocation which is already freed, then it will be a seg fault. And I don't really see the point of letting the program crash in such an occasion. It must be better to just return a false, right? So that's what we'll do. So bool destroy, and we're going to provide this with a pointer, same as the free function. So basically we give a pointer to the first word of the allocation that we want to destroy. So this will basically be, let's see, it's not a header. I guess we can call it a word, maybe. What does the alloc function return? It returns a void star. Perhaps we should go with that then. So void star as the only argument, like so. And I also want to annotate if the functions we are writing is going to be exported or not. So I'm going to do, let's see, let's create a definition which is public, and this will be an attribute where we set, is it visibility? I'm not sure really. Let me just double check real quick. Let's see. Where did I put it? No, it's inside of this. So let's see. I think I have it inside of the os api.h. Maybe, or os.h. There it is. So visibility default. Okay. It's a tough one to remember, that one. And that basically means that this will be exported as a library. So visibility default, like so. And then I will create another definition which is called private. And here I will just define it as static, because static functions, they are in the same namespace as the C file, basically, as the translation unit. So that's pretty much like it's private. And this destroy, that will be a part of the public API. So I will annotate this public. And the show function, no, I don't think I will export that. Find block is an inner function. Same with make allocations. The alloc function that is most definitely public. And the main, we're gonna remove main when we are done, so I will not annotate that at all. And by the way, while we're at it, the reason why let's see, that I just named this alloc is because I want to create aliases. So let's say we have a macro which is named alloc k, and this takes an argument x, and what it does is it allocates 1 kilobyte of memory, or x number of kilobytes. So basically it will call the alloc function providing the x times 1024. And I will also create one alloc m for megabytes. So this will call alloc with the x times 1024 times 1024. That's megabytes. So this will make it a little bit easier when you want to allocate bigger portions of memory. It would be kind of cool to have 1 gigabyte as well. Maybe we should, just for the fun of it. So this will be alloc g. We take in an x, and this will call alloc m, let's say, with an x times 1024. That should be possible, right? And why do I put this x inside of parentheses? That is because perhaps we're not going to give a number as an argument or a variable. Perhaps we will give an expression, and we do want to support that. All right, so before we forget, let's add this annotation to all of the functions. So find block, that is private, and make a lock, that is private as well. This is most definitely public. The show function is private because it's mostly for debugging while developing. And then we have main, which is nothing. All right. Right. So where were we? Yes, we're going to create this destroy function. And it will be pretty simple, I guess. The only thing really that we need to do is find the right block and change this allocked boolean from true to false. But due to security reasons, I want to zero out that mem space, so it doesn't follow another allocation, and then you are able to read parts of the memory where, I don't know, sensitive things are stored. I think that's a good way to deal with things, even if it's strictly not necessary. All right, so let's see. Public bool, and this is called destroy, and it takes a void star address, let's say. So first of all, we need a header to be able to read in those things, and we can calculate the position of that header because the address is the first word of the actual allocation, which means that we go back one word and we are at the start of the header. So let's also define a void mem, and we set the mem equal to address, and we set, maybe we don't need this since both are void pointers. Let's try go at the header directly. So P should be equal to the header cast address. And maybe we need to do this. And then we take -4 bytes. And then we should be at the correct place. So what do we need to check? We want to see that the W, the number of words, is not 0. Because then we are trying to provide the wrong address. So if maybe we can use the same syntax as before. So if PW is 0, or if alloc is false. So if this space is not allocated, then we also want to treat it as an error case. And what do we want to do in this case? We want to return an error. And what should we call this? Double free, perhaps. So error double free, something like that. And let's add this to our list of definitions. So we will have an error double free, which is 4, and let's also create a no error case. So no error, and this is 0, like so. Okay, and I think this is the only thing we are gonna check. So now we wanna zero out this whole mem space. And do we have access to birch utils? Yes, we do. So then we can use the 0 function in birch utils. And if you don't have the birch utils library, make sure to download that from the repo. All right, so let's see. We need to calculate how many bytes we are going to zero out. And this is pretty easy. Let's do an int16n. And we'll set n equal to the number of words times 4. So that's the number of bytes we want to clean out. So then we just call the 0 function. We provide the address cast to a int8, and we give it the n as is. So now this one is clean. Now we can alter the header. So we'll set the alloc. What did I call that? Alloced. All right, I need to change this allocked. So allocked should be false in this case. We will leave the W as is so we know how big this hole is in case we want to allocate this again later on. And that's basically it. If all this is done, then we can return true. Simple as that. All right, how can we test this? We have 3 allocations. Let's say what do I call it? Destroy. Let's say we destroy P2, the big allocation in the middle. And let's save the return value of this. So we'll do a bool ret, and we set ret equal to this. And let's print the return value. So ret equals, we take a string here, and then we can just do a ternary. So if ret, then we return true, otherwise we return false, like so. Right. And let's do a 4th allocation after we have freed this, and let's see if it positions itself in the middle. That can be interesting. So we do a P4, and P4 is equal to alloc. Let's do 1800. And then we show the allocations and return. All right, let's see if this compiles. No, it did not. Statement with no effect. We don't like those, do we? I think I forgot that I didn't make it as an as an if statement. And we do not have any else case here. But never mind, let's do this anyway, just for the fun. So if this is true, then we return this. Otherwise, we do void 0. That should work, right? Expected expression before. What did I miss? There are several lines in between here. So let's do a parenthesis and a curly brace. And we need to end those as well. So this, and then this, and this. This should work, I think. All right, some warnings about unused variables. Nothing to care about. Let's see what we get. Return value is true, which means it managed to do the allocation. So one is 2 free words. And here we have 500 allocated words. 1 allocated word and 450 allocated words. Let's do some calculations where we take all of these values and times it by 4. So we have it in bytes instead, because bytes is what we give to the alloc function. So we have 8, 2000, 4, and 1800. So this is 8 because it rounds up to the nearest word, and 2000, and this rounds up to 4, and this is 1800. But it looks a little bit weird because we have these 3 allocations, and in the beginning we have 2 free, well, a whole basically of 2 words. So something's not right. Either we are deallocating the wrong thing, or there's something else weird going on. So yeah, let's see what result we get if we don't destroy this thing. Alright, then all 4 of them are allocated. So basically we deallocated the wrong thing. How is that possible? We deallocated the first, right? But we gave it P2 as the wait a second. Maybe it treats this each step as a word, probably. That's it. And that's why I should have done what I first thought of, creating this intermediary variable. So let's see. It's this one. So let's set mem equal to, and we take the same thing, and we minus 4. And then we set p equal to, maybe we shouldn't cast this. And then we set p equal to the header cast mem space. This is the right way. Alright, so let's see what happens this time when we destroy the second allocation. Same thing. It frees the first. Why does that happen? It's pretty weird, no? Maybe we should print the addresses as well when we do the show. So let's see, where is our show function? Here. And we don't have a field for that address. We need to calculate it based on pointer arithmetics. So let's see. Maybe we can put the address in front here. So it'll be 0x% dot 08x. And what do we give it as argument? Let's see. We have a P which is pointing towards the header. So if we were to do a conversion to an int 8 of P, then we should be able to take this and add 4 bytes. I think this is the right thing. We can verify it by printing one of the return values manually. So let's print the first right here. So P is equal to 0x% dot 08x. And then we just do an integer cast of P. Like, no, this is not right. This is how it's supposed to be. And maybe we need to do the same here. So we convert it into an integer. Alright, so P is this ending in 24. And this is the address of the first allocation. Which means we are giving this to the destroy function. But why doesn't it? Let's double check our code here. So what do? We set the mem equal to the address -4. And since this is a void star, that should mean 4 bytes, right? We set P equal to that location. Ah, I forgot to remove the old one. Okay, let's try this again. Now we're talking. We're one step closer to the solution. As you can see, this allocation got freed. But when we did our new alloc, this one for 50 words, it did not position itself inside of this hole. So that's a bug, and we need to figure out why. So the thing in charge of finding the block to use for the allocation is this find block function. And it takes a current header, the number of words to allocate, and a counter, how many words we have, how many words we have traversed this far. So let's see what this does. First we do a check that we are not past max words. And if so, we set OK equal to if the current header's W number is false or 0, then we set OK to true, but it should not be 0 in this case. So then we check if it's not allocated, and that is okay. And then we check if the W is more or equal to the allocation. And this is 500 or something. Yeah. And the allocation is 450. So this should also be true, which should make this true. And if it's okay, we return that header. And where does this find block start? It uses this alias or macro that we defined, find block. So it takes the mem space, so the beginning of the heap, and the counter is 0. So it should find that correct position. Maybe it's the same bug here, that the pointer arithmetics is failing. Let's see, we set mem equal to v header, that's void header, and we add the w times 4, and then we plus 4 to it. So let's see. This is the number of words, and this is the number of bytes to the next header. Should we really have plus 4 here, I wonder? Because if we're at a header and we jump the number of words of the allocation, we should end up in the next header, right? Because if we jumped from the first position of the mem space or the allocation, then we were to jump to the next memory space. So I think I'm going to remove this 4. Let's see if that makes a difference. It did, but not in the right direction. Now we only get one allocation and then it fails. Maybe we can try to add some typecasts to this stuff. Instead of making this a void, let's make this an int 8 for now. So the header as an int 8, and then the header w times 4, and we plus those together. Maybe we can even do this. And the result of this whole thing, that we can cast to a void. Does this make a difference? Invalid operands to binary plus have int 8 star and int 8 star. Okay. That's a little bit weird. If it has 2 pointers of the same type, why shouldn't it be able to plus those together? That's pretty weird. What if we just leave this out? Okay, then it compiles at least. But we have the same problem. What if we add this 4 now? Alright, we're back at where we started. So why doesn't it use this one? Maybe we can add some debugging. If we add a print, and we print the address of the pointer to the header, so we do this, then we should be able to see which one's which. Can even do something like trying in this address. Okay, so it starts at the beginning of the mem space. It tries to see and then we run it from the beginning again. So this is the second allocation. It goes to 2C and it goes to 800. It is off by 4, isn't it? 22C, 800, 808. So it should, let's see, it starts at 20. So this is the last allocation. And it should go from 20 to 24, right? Or no, we are comparing apples and pears. This is actually the address of the headers, and these are the addresses of the allocations. So let's do something of this magnitude. No, plus 4 it should be. Okay, so this is more accurate. Okay, let's try this again. So first it tries 24. And that's the 2-word block. Then it tries 30. and 30 has 500 free words, so this should go through, but it doesn't. Instead it jumps to the third one and then to the end of this allocated space. So there must be something wrong with this if statement. So if W is 0, which it's not, so this can't be the case. If alloced is 0, and it should be, right, because we set it to false, and the W should be more or equal to the allocation. What about this then? If n plus allocation, and n should be 2 at this point, plus 450, so 452, if that is more than max words minus 2, and max words is, well, it's a lot, 250k or something. So it shouldn't be this one. And since it continues to look, we must end up at this else. That's right. This is a little bit reversed, because if this is true, then we return that header and allocates accordingly. So we want it to return true. What is wrong here? Well, let's print some more debugging stuff. Let's see what the OK is. So we'll do the same thing here, a ternary. If OK is true, then we return true. Otherwise, we return the string false. So now we should see a little bit more what's going on. Alright, so it tries 30 and OK is false. So that's the problem. But why does it return false? Because this should be 0. And I can't believe that the W is not bigger or equal to the allocation. But let's print all the values so we know. So header W is either true or false. So let's do the same here. Can even copy this part. And let's also print the header. Wait a second, W is not a boolean. Let's say this is allocked instead. And it should be header allocked. And here we can print the W. And let's print it as a regular integer. What else? We should print the allocation also. And let's do that as an integer as well. Allocation, like so. Let's do 2 spaces here so we get a little bit of separation. All right, now we should get a little bit wiser. So trying 30 is the interesting thing. So OK becomes false. W is 500. Alloc is true. Why is that? That's weird. Because we set P allocked equal to false here. And we set it to the address provided -4. Are we trying to free the right thing? Let's add some debug message. Freeing address with header, and then we give that as well. So the first is going to be the address provided. The second one is P. And let's add a new line as well. And maybe highlight it a little bit. Alright, so freeing address, blah blah blah, 30. With header to C. And that sounds about right, doesn't it? Maybe I am calling this in the wrong way. Yes. Okay, we have been troubleshooting for half an hour, and the reason is I put this call before I destroyed this. Let's change these two, and let's remove all of these debug messages. Yes. Let's see, I added a lot of printfs all over the place. Let's clean those out. This one we keep. Alright, now let's see if this works. So we make clean, jump down a little bit, clear the screen, we run make, and boom. Okay, we got a different result at least. So now this new allocation is put into the hole. But what happened to our last one? I mean the previous last one, P3. It disappeared. Let's see how this show function works. We set the memory address to the current P. And we plus the number of words plus 1. And we times it by 4. And then we set P equal to mem. And where do we start this thing? If we check on the macro, Mem space is the first thing. So the header is a mem space. And we should have a W all the way. Unless we overwrite that somehow. Could it be that we calculated the number of bytes zeroed wrong? So we zero it by n, and n is W times 4. From the point of address. That should be right. Maybe we can do a show before we destroy P2. So let's see, we have these 3 at that point. Then we remove this and we put in this. But allocation number 3 seems to have disappeared. Let's add a debug message for the free function. So let's do something like address equals this and n is equal to this. So address should be like this and n should be like this. So now we can see if we are calculating this correctly. Alright, so the address that we want to clear begins with 30. And that's this one. And we're going to clean 2000 bytes. So basically the last byte that we're going to clean will be this number plus 2000. And if we turn this back to hex, we get this C800. So C804 is the third allocation. And is that the header or the mem space? So let's see. This is the first. P plus 4. This is the mem space. So the mem space begins at 804 and 800. That should be the last header. So we are off by one word then, I think. So let's do this -1 times 4 and see what happens. We get the same result. Well, we can't possibly overwrite this time. What if we were to show it before we do the last one? Okay, so it's there. And I doubt that the last allocation is affecting this header in any way. Because it's obviously not the destroy call, since that happens first, and then we print this. So it must be that something goes wrong. Or is it how we calculate it when we traverse it for the show? Because we are going to loop as long as we have a W. Do we have a W at each step? We should, right? Well, we see it here. We have a 2 and a 500 and a 1. And before we had the 2 and the 450. Wait a second. We deallocate this 500 space, and then we replace it with this 450 space. But the new hole of 50 words in between, we haven't specified in any way. And we changed the W from 500 to 450. So what we need to do is when we create a new memory alloc, we need to we need to create a new header in the hole that we are causing. So how do we figure out if we actually is leaving a hole? Because this is simply finding the first header that matches the criteria. And it returns the address to the header. Well, maybe. Let's see how it does this. It finds a block, it checks that it has an header. And it compares the words that it wants to allocate. And then it makes an allocation for that header. And what does this do? This changes the W. But what we should do is we need to check if this is a whole or not. So we can compare if words is more, let's see, no, if the current W is more than the words we want to allocate, then it will leave a hole. So let's create a variable and let's say the difference. We set the difference equal to the current W minus words. So we have two possible cases here. Otherwise, on the one hand, it can be 1, and then we need to add an empty header so the traversals don't fail later on. And if it's more than 1, we need to add a header for the whole. So let's see, do we do that differently? Let's write the code for the usual case first, if there actually are more than 1. So in that case, we need to have a new header variable. So let's do something like mem and header. What should we call this? Header prime, perhaps? Alright, so let's see. Mem should be equal to the current header plus the number of words times 4 plus 4, I think. So this is where we want to put our new header prime. And we want to set its W equal to the difference minus the header. And we want to set alloced to false, because this is a whole. So if diff is 1, what will that mean? That will mean that W becomes 0 with a locked false. That means that both of these are 0. And that will make it get treated as the end of the allocated space, which is not good. So we need to give it some special meaning value. What about the maximum number? Because we can't allocate that much anyway, since we need to leave room for the header. So we set this to if we don't have a diff. Let's do this. Diff minus minus. So if we don't have a diff, set this to -1. Otherwise, we set it to the diff. Maybe we should use a constant here instead. So let's call this let's call it 0 words. And we go over here and we define 0 words to be a word casted -1. And -1 is all ones binary. It's the biggest number that variable takes. And since we have 30 bits here, that should be something like, let's see, 4 billion, 2 billion, 1 billion. Yeah, we can never allocate that much. Alright, so now I think the rest of our code should work. We need to look out for this case though, and we don't have to do any if statements. Header locked, and we need to change the right thing. This should be the new header. It's false, and then we have the reserved, which we won't do anything with. So now we have created that extra thing, and then we can continue as usual by returning the first header. So I think this is going to work. We do need to check our other functions though, and see if we need to add some extra code for this max int thing. So let's see. This should not be a problem. Remove this print as well. Find block. So what do we do here? This can be a problem. Maybe we should do something like this. We create a word called W. And W we set to if the header W is equal to, what did we call that constant? 0 words. Then we set this to 0. Otherwise, we set it to W from the header. And then we can just replace all of these occurrences. No, not this. This though. So in this case, the W will not be sufficient for the allocation. What about this? Mem is equal to the header. So the current header plus 0 times 4. Plus 4. And since this is a header followed by another header, this should be correct. And we set n equal to n plus 0 in this case. And then we did this. I think this will work. But maybe we should use the right thing here. We need to use W, not the other way around. And same here. Alright, this function is okay. What about this? Make allocation. Bytes in words in words is more than max words. W. This is okay. And this, if words is more than max words, no, we shouldn't have to change anything here. What about here? Here we do need to do the same trick as we did in the other occasion. So put this p is equal to header w is equal to if p w is 0 words. This should be 0, otherwise p w. And we don't want to stop the loop here, so here we can use this. But here we should use this, I think. W plus 1. So this will be 1 times 4. Yes, that is how much we want to jump. P is equal to mem, blah, blah, blah. And this should be W instead. Alright, I think that's it. Let's see what happens. It didn't quite work, did it? Two free words. Two free words. Because we create these, we destroy feet 2, which is this big thing, and we replace it with this. Now we only have 1, and then we have 2 free words here. I wonder if we messed up a lot. So let's see, it's the same here basically. We only have 2. What if we make this bigger? Does that matter? Okay. No, it didn't. But it's always 2. We must have miscalculated somewhere. here perhaps. So we set the W. If PW is equal to this, then it's 0. Otherwise, it's PW. We loop according to PW. Memory sets to W plus 1 times 4. It can't be this print function. It must be somewhere else. And it's probably somewhere here. So let's see, if the W of the current header is more than the words, then we calculate the difference. And we return the header plus 4. So the header plus 4, that's the beginning of the memory space. And if we take the W times 4, we should get to the end of the new allocation. Yes. And if it's 0, we'll set it to this, otherwise to the difference minus 1. I think this looks right. But there is a problem that shows even before we delete and reallocate. So it must be somewhere else. Here maybe. we check if the W is 0. Which it is in this case, but it shouldn't be checked against that. So here we should actually have the header W. In this case though, here it makes sense to have the W because we want it to be 0 if it's empty when we do the comparison with allocation. And when we calculate the memory address, then we take the current header and the W times 4. And if this is 0, we only take +4 from the current header, which should be correct. And then we plus 0. Let's see what happens after this change. Still the same. 2 allocated words. So why does it set to 2? PW minus 1. If this is 0, or if this is 0, or allocated is false, then we return an error. Otherwise we take the number of words minus 1. But this shouldn't be the case anyway, since we will not try to free this space. So we should treat this as, yeah, I think we'll do that. This won't fix the bug we're looking for, but it will make this a little bit better anyway. So we do it as we did before. We do a ternary where we check if this is 0. If so, we return 0. Otherwise, we return itself. And we will use that for this if check. about here? Well, we shouldn't get this far because this will give us an error. So it doesn't really matter how we use it here. But let's say we were get to this point, and the W is 0. So 0 minus 1, that overflows that integer and puts it into max value times 4, and that will totally bug out. So let's use the W instead. No, wait a second. It's if we use that W, then that will happen. If we use this instead, then we will start with a max value minus 1 and times that to 4. So both ways are weird at that point. But this should prevent that. So let's not put too much work into that. What if we go to this here, and instead of printing the W, we print the PW. Okay. But that means that it calculates the W wrong. If PW is equal to 0 words, then it's 0, otherwise PW. So why did it become 2? Here we have W plus 1 times 4. But here we just had the W. It's really weird. Why did it become 2? This is 2. Oh, wait. Huh. I set this here before the iterations, but I don't set it at each iteration. So I need to have the same thing here. Okay, I believe we are closing in on the error. Hopefully. So let's see if this is 0 words, it becomes 0, otherwise PW. W, which means that this should now work. Um, oh, we need to do this. Okay, that's more like it. So first we have these blocks. Um, do we have 2 blocks in a row of size 2 words? No. This is 500. It's this. But why do we have 2 of those? It's almost as if it triggered the let's move this down here so we see what happens after the last one. Okay, so this is what we end up with. We have this, and we free this, and then we do what exactly? We should create one more, the 451. No, we are doing this wrong. I think the problem is that we are putting in this extra header when we really shouldn't. So let's see if this W. So this is where we want to do the allocation. So if we have a W, which is more than the words. So this could actually be an empty header, right? But I don't think that's the problem here. So in this case, we want to jump to the next position. Let's double check how we jump to the next position in the other cases, like here. So the current header plus W times 4 plus 4. W times 4 plus 4. We do the same thing, but we cast it a little bit differently. Don't know if that has any meaning though. this should be inside parentheses and the whole thing too. But as I said, I don't think that's a problem. No. We need to do some debug messages. So here we're inserting new header. And let's say the address is this. W is this. Locked. I will just do it as an int now. This is header prime. This is header prime W. And header prime allocated. Okay, here we actually put one in. 49. But that's actually right, because we remove this, which leaves a hole of 500. So when we add the 450, there is a 50 gap. Is the address right then? 800. It should be more, right? Because this block that we removed starts at 800. But this address should be 450 from that, right? Allocation. Because we are returning this one. Well, when we calculate this memory address, we should not start at this current header, but the next one. And this is still 500. So maybe we should use the difference here instead. Okay, so this time we end up at F8. That's a very long way past, isn't it? But maybe it's right. If we take this and let's see, so the header will be at this address, and we want to jump 450. Okay, so we want to end up at 9C2. But we don't even get close to that. So basically we should not use the difference here, we should use the words of the new allocation. That's right. And +4 is for the header we're at. Yeah, this could actually work. Okay, now things are starting to happen. So we have this, then we have a whole of 450. And then we have an allocation of 50. Well, first of all, why does it show these as 2? We had that problem before, didn't we? When we used the W. Because we set it to this. And we did that. And then, maybe I did it in the wrong order. Let's take this whole thing. And let's put it here instead. Alright, that should be better. So the first is 2 and 500 and 3. That's right. This. Then we insert a new header. So we have this for 50 allocation, which we make here. And that leaves 49 free words and a new header. And this allocation that we made here, number 3, persists, but is now positioned at the end. Everything is working. What do you say about that, huh? Pretty nice, if you ask me. Pretty nice. All right, so let's clean this up a little bit, see if we have any printf statements that we do not need. This we will keep, and that is the only one left. All right, nice. Can remove that too. So now we can make memory allocations. We can free them. We can make new allocations where we put the new one inside of one of these holes. Yeah, we can pretty much do it all. Let's try, by the way, what if we were to make one of size 1999? That leaves one word, which will be the header. Let's see if it handles this correctly. So we have this and that. Oh, wait. these are bytes, not words. So we need to do this. Oh, that would constitute as a bug, I would say. Very weird one. Is it just a show loop, which is buggy, or... Maybe we can list from the beginning. Okay, so this is okay. Then we have the 499. Then we go to the 0 case. And that's when weird things start to happen. So PW, if it's 0 words, then it's 0. Otherwise PW. And here we have 0 plus 1 times 4, and we add that to the memory. That should be right. Wait a second, I think I remembered something now. Um, I know what it is, but I'm not sure where it is, the error. Ah, here we check it for a 0. And we check if PW is 0, then we set it to 0. That's not right. We should check it against, what's it called? 0 words. That's the one. And here we do the right thing. Maybe the problem is that we use the -1. I guess that, or -2. I guess that means different for different data types. And maybe that's why we get into trouble. What if we just do this? There we go. So we have these two. We have 499. And the ones that left is an empty header. at FC, yeah. And then follows our last allocation. Okay, so now everything works. Every little thing is working. So, yeah. But this will be all for today. If you like this episode, please like and subscribe, and we will continue this project in a later episode. Thanks for watching. Thanks for today.